Okay, so we've got the notes for section 4.2, trigonometric functions of acute angles. So we have to start with some right angle trigonometry. So some definitions. Geometric figures are similar if they have the same shape, even though they may be different sizes. Having the same shape means that the angles of one are congruent to the angles of the other, and the corresponding sides are proportional. So for example, all squares are similar because the angles in the corner are all 90 degrees. One may be very large, one may be very small, but all squares are similar. Same thing for equilateral triangles. They all have 60-degree angles, so they all must be similar to each other. Down here it says acute angles are often put in standard position in the xy plane with the vertex at the origin, one ray along the positive x and the other ray extending to the first quadrant. So what that means is if you draw an angle, so here's our coordinate axis, the vertex sits at the origin, one side of the angle lies around the positive x, and the other side goes off into quadrant 1. Now, it says acute angles, so it has to be in quadrant 1, because if you rotate it farther and go into quadrant 2, 3, or 4, you no longer have an acute angle, you have an obtuse angle because it's more than 90 degrees. You're always rotating that direction. Okay, and then down here, definitions of the trig functions for acute angle ABC. So our triangle here, so I didn't put a figure on here. So this side is referred to as the opposite, this side is the adjacent, and this side is the hypotenuse. You're talking about this angle down there. So these three you are probably familiar with, sine, cosine, tangent. Over here you have, there are actually another three, the cosecant, the secant, and the cotangent. They are the reciprocals of these. So if you notice, sine is opposite divided by hypotenuse, and cosecant is hypotenuse divided by opposite. So each of these three are the reciprocals over here. So we normally organize them this way, so it's just easy to do, because once you calculate these three, you just flip the fractions, and you have these three. All right, so example 1, find all 6 trig for an angle of 45 degrees. Okay, so here's my triangle, here's my right angle, so here, the right angle is always down there. So remember, hypotenuse is always across from the right angle. So if this angle is 45 degrees, this angle is also 45 degrees. So if you notice, it doesn't give me any side length, so I can choose whatever I want. Now this, even though it's tipped, is an isosceles triangle. The sides opposite congruent angles are always congruent. So I'm just going to make them both 1, because why not? So I need to find this missing side there. This is a right triangle, so the Pythagorean theorem is true. 1 squared plus 1 squared is the hypotenuse squared. So 1 plus 1 is c squared. 2 is equal to c squared. So c is the square root of 2. So there's my triangle. And now I can just use my definitions. So the sine of 45 degrees is equal to the opposite divided by the hypotenuse, 1 over root 2. Now you are not allowed to have a root on the bottom of a fraction. To eliminate it, you multiply the top and bottom by that root. So on top I have root 2. On the bottom, root 2 times root 2 is root 4, which is just 2. Essentially you're squaring here, multiplying something by itself, which cancels a root out. So cosine of 45 degrees is adjacent divided by hypotenuse, so 1 over root 2, which once again we can't have, so it's the same thing, 1 over root 2. Tangent of 45 degrees is the opposite, 1 divided by the adjacent 1, so it's just 1. So there's the left 3 here. So do the other 3, cosecant of 45, secant of 45, and cotangent of 45. So these are the reciprocals of these. Now, I could flip this over, root 2 over 2, and get 2 over root 2, but then I would have to rationalize again. But I can also flip that one over. If I flip 1 over root 2 over, I just get root 2 over 1, which is root 2. Same is going to happen here. This is also root 2. Reciprocal of 1 is 1. So there's your 6 values. So when you go to do the reciprocal step for these 3, don't think that you have to reciprocal your final answer. You could go back and to any place that you have reduced or something like that. Typically for cosecant, secant, and cotangent, if there's roots involved, you want to flip the one over that has the root on the bottom from its partner. So I wanted to flip this one over, because when I flip it, the root comes up, which means I don't have to do this multiplication step again. Okay, so 30 degrees. So we'll draw a triangle. So here's 30 degrees. There's my right angle, which means this is 60 degrees. So this is a 30, 60, 90 triangle. So the rule for a 30, 60, 90 triangle is that if this side is 1, this side is root 3 times that, and this side is twice that. And if you check, 1 squared plus root 3 squared is equal to 2 squared. This is true, 1 plus 3 equals 4. That is an accurate statement. But same thing, so we'll do our trig functions. So sine 30, cosine 30, tangent 30. So the sine of 30 is the opposite over the hypotenuse, so 1 over 2. Cosine is the adjacent over the hypotenuse, root 3 over 2. Tangent is opposite over adjacent, so 1 over root 3. But that's not allowed to happen, so we multiply the top and bottom by root 3, which gives me root 3 over 3. And now they're partners. Cosecant, 30 degrees, secant of 30 degrees, cotangent, 30 degrees. So cosecant is the reciprocal, so the reciprocal of 1/2 is 2. Reciprocal of this is 2 over root 3, but that's not allowed, so we do root 3 on top and bottom, which gives me 2 root 3 over 3. For cotangent, I can either flip this one or that one. I'm going to choose this because the root's already on the bottom, so it just becomes root 3. Now when you do these, we're working with roots. We're not doing the decimal equivalents, so don't give me 0.86 for this, is root 3 over 2. Not 1.7 for this, root 3. Okay, so example 3, let theta be an acute angle such that sine is 5/6, evaluate the other 5 trigonometric functions. So draw your triangle. So right angle there. So I know sine is 5/6, and my angle always sits down here. So sine of some angle is 5/6. So I also need to find the cosine, the tangent, the cosecant, the secant, and the cotangent. Now I can actually do cosecant without doing any more math because these are reciprocals. The cosecant is 6/5. Flip the fraction over. Now to get the other ones though, I don't have enough information. But what I can do is solve this triangle. If sine is 5/6, that means the opposite side is 5 and the hypotenuse is 6. So I need to find that missing side. So 5 squared plus b squared is equal to 6 squared, Pythagorean theorem. Please be careful. The side you're solving for is not always the hypotenuse. Make sure you put it in the right place. If it's a leg, connects to the right angle, it goes on the left. If it's the hypotenuse, it goes on the right. So this is 25 plus b squared is equal to 36. So 36 minus 25 is 11. So b is the square root of 11. Now I can finish. Cosine is adjacent over hypotenuse, root 11 over 6. Tangent is opposite over adjacent. So a bit of a shortcut. I would have to multiply top and bottom by root 11. When you do that, essentially what happens is the root moves up and the number stays behind because you're going to square root 11. So over here, this is going to become 6 over root 11. Flip that one over, which becomes 6 root 11 over 11. The root moves up, the number stays behind. So for cotangent, I'm actually going to flip that one because when I do that, the root comes up, which is where I want it. So root 11 over 5. Okay, applications. So using some parts of a triangle to solve all the other parts of solving, which is what we just did up here. A right triangle with a hypotenuse of 8 includes a 37-degree angle. Find the measures of the other 2 angles and the lengths of the other 2 sides. So let's see here. So we got this. So we'll put our 37 degrees down here. There's our right angle. Hypotenuse is 8. Find the other 2 angles. Well, okay, so there's one. So one angle is 90 degrees. The other angle's up here. So you have to remember that the angles in a triangle add up to 180. So we would take 180 minus 90 minus 37, which is 53, I believe. 180 minus 37 minus 53. Yep. Whoops. 180 minus 90 minus 37, yes, is 53. So the missing angle is 53 degrees. Now, what we can actually do though is, since we have a known angle and known sides, we can actually use the sine, the cosine, or the tangent to get one of these other two missing sides. So for example, if I wanted to find the opposite side here, I'm going to use angle 37. Opposite and hypotenuse are sine. So the sine of 37 degrees is equal to the opposite divided by 8. Now I can do that in my calculator as long as I make sure my calculator is in degree mode. So the sine of 37 is 0.6102. It's equal to x over 8. They multiply both sides by 8. So x is equal to 4.81. And then I can use, now I can either use Pythagoras or use cosine. Call this guy y, is y over 8. Well, the cosine of 37 is 0.799 equals y over 8. So multiply that by 8, and we get the other side is 6.39. So we found the other two angles, 90 and 53, and we found the other two sides, 4.81, 6.39. Okay, so example 5. From a point 340 feet away from the base of the Peachtree Center Plaza in Atlanta, Georgia, the angle of elevation to the top of the building is 65 degrees. Find the height. So let's draw a picture. For trig problems, it's always a good idea to draw a picture. So we're finding the height. We know this distance is 340 feet, and we know the angle we're looking up is 65 degrees. So we have to pick one of our trig functions. We know that's a right angle. So from the 65 degrees, we have the opposite and the adjacent, so that is the tangent. So I know that the tangent of 65 has to equal h over 340. So we can multiply 340 both sides, so 340 times the tangent of 65 is equal to h, and then I can just put that whole thing in my calculator. I don't actually have to work out the tangent of 65 as a decimal first. So 340 times the tangent of 65 comes out to be 729.13 feet tall. That's how tall the building is. All right, so that brings us to the end of this section.